So, welcome to Intro to Stats. This is week 3, and we're going to start off with a review of week 2. So, last week, first things we went over were types of bias as we looked at the introduction to data collection and probability. There are a couple different types of bias. Not important that you know them all, but you should be able to recognize when there is bias. So, for example, some of the more common ones are just sampling bias or undercoverage bias, where you don't get a representative sample of the population that you're trying to gather information about, or like question wording bias, where the way that you word your questions leads towards it influences your group to a specific answer. And then we went over some sampling methods. So there was a simple random sample, which is exactly what it sounds like. It's simply taking a random sample. It's completely random. Then there's the stratified sampling, which is where you split your sample into groups based on a common characteristic, and then take a simple random sample from within each group. Then there's cluster sampling, which is where you split your sample into groups randomly, so they're not based on a characteristic. And then you take entire groups instead of taking parts of each groups. And then there's also systematic sampling, which is basically taking every kth person. So for example, if you assign each person a number from 1 through 50, you could take every third person and sample them. And then we went over some experimental vocabulary and experimental designs. Those are not really important for you to know, but they are linked on the last slide. And if you want to reference that again, you can look at the recording from last week. Then we looked at some basic probability rules. Here's just, again, you don't have to memorize all these, but some of them are good to know. The complement rule. This one is one that's pretty intuitive. So this is just the probability of an event happening is 1 minus the probability of the event not happening. That's pretty self-explanatory, right? Then here are some rules for multiplying probabilities. Here's some rules for union of events. So basically the chances that 2 events both happen. And then here's conditional probability and the Bayes theorem. And then of course, the law of large numbers. I just wrote that in to remind you, probability, what that means is the long-term ratio of an event happening. So basically, if you flip a coin 2 times, right, it might not be heads and tails, right? It might not be a 0.5% like frequency, 0.5 frequency of getting heads or 0.5 frequency of tails. But if you flip that same coin instead of twice, you flip it hundreds of thousands of times, right? Or let's just say 300,000 times. It's going to be pretty close to 150,000 heads and 150,000 tails, because that's getting closer to the actual probability. The more times you run a trial, the closer the frequency of an event happening gets to the actual probability of that event happening. That is the essential claim of the law of large numbers. All right, so that is the review of what we did last week. Before we move on, I just want to see if anyone has any questions. If you do, feel free. What was that? I heard. No, go ahead.
I said I don't.
You don't have any questions. Okay. Yeah. All right. Well, if anyone does, feel free to unmute your microphones or put it in the chat. If not, then we will move on to week 2. Week 3. That is a typo. It's supposed to say week 3. All right. So week 3, probability and sampling distribution. So we're going to continue probability, which we did a little bit of last time. So we're going to start off looking at combined sets. So basically, if you have a set of data and you calculate some statistics for that, right? You can get the mean for that data and you can get the variance for that data. And then you take a different set of data and you calculate the same statistics for that set, like the mean and the variance. But now you're thinking, okay, what if I want to combine both of these sets and I want to know what the mean and the variance for this new set, this combined set is? Do I have to go through and add every individual value and then subtract by the number of numbers again to find the mean? Or is there a simpler way? So yeah, there is a much simpler way. When the sets are independent, what you can do is take the mean of the first set and the mean of the second set and just add them together. If you're adding the two sets together, all you have to do is add the means together and you get the new mean. If you're subtracting the second set from the first set, it's exactly what you'd expect. You subtract the second mean from the first mean. Variances, this is a little bit surprising. The first part of this makes sense, right? If you're adding the two sets, then you add the two variances. The second part is a little bit, it's going to seem counterintuitive, but if you subtract the second set from the first set, you still add the two variances. It doesn't matter whether you add or subtract. You will always add the two variances when you're trying to find the variance of this new combined set. And this does not always apply. It's important. It's the general rule. And this, first off, never works if it isn't independent. But all these same rules, or rather these same tendencies, because this doesn't always work, they all also apply for random variables. So not just combined sets, which is basically two separate sets of data that you either add together or you subtract one from the other. It also applies for random variables, so probability-based variables, which is like this table that we looked at last week, where you have these different values of X. These are all different possible outcomes. And then you have the probabilities of these outcomes. So say we have a four-sided die, right? I don't think that's possible. It might be possible. Yeah, like a tetrahedron. So we have a four-sided die, and it's a weighted die. So there's different probabilities for it landing on each side. Then the outcome, that would be a random variable. So there's a 0.2 chance that it lands on 1, 0.4 chance that it lands on 2, 0.3 chance that it lands on 3, and 0.1 chance that it lands on 4. That's just a quick reminder of what a random variable is. If you have,
what do all these chances mean? Like, why is one 0.2 and 2 0.4 and so on?
Oh, so the reason, are you asking the reason for these specific values? Like why is one have to be 0.2 instead of something else?
Yeah.
Yeah, so these numbers are actually just made up. This is just to show an example, but one doesn't necessarily have to be 0.2. It's just for this example. Does that answer your question?
Yes.
Okay, great. Thank you for asking. If anyone else has any questions, by the way, please feel free to ask. All right, so that's just a quick reminder of what a random variable is. Now, if you're trying to combine two random variables, you take the means, the expected values of both, which the formula to calculate we had last week, basically you multiply each number by its probability, and then you add them together. If you have the expected value for two separate random variables and you want to find the expected value for a combined random variable, you do the same thing. You add it together. And if you want to subtract the second one from the first one, then you subtract the second expected value from the first expected value. Now with random variables, just like with combined sets, for the variance, regardless of whether you want to subtract the variables or add the variables, you have to add the variances. And again, this is a general rule, does not always apply. All right, so the next thing we're going to look at is transforming random variables. So as we said, if you want to add something to each value of x or subtract something to each value of x, right? So for example, if we were to add a constant like 5 to each of these, so instead of this being a 0.2 chance of landing on 1, it will be a 0.2 chance of landing on 6, and this would be 7, 8, 9, right? If we wanted to add that, then it would do the same thing to the expected value. We would take the expected value of this, which I think we calculated last time was 2.3, and we would just add 5 to that. So now the expected value is 7.3. If we wanted to subtract 5, so then this would be -4, this would be -3, -2, -1. Now the expected value is 2.3 minus 5, which is like -3.7, something in that range. -2.7. So that is, you just simply add it or subtract it. The variance or the standard deviation, that does not change. So if we want to add 5 to this, and then we want to add 5 to this, and this, and this, and it becomes 6, 7, 8, and 9. The variance is still the exact same as before, and the same thing with the standard deviation. So if you want to add or subtract from a random variable, you do the same thing to the expected value, but you do nothing to the variance of the standard deviation. It stays the same. Now, if you want to multiply by a constant, so if we stick with 5, we're going to multiply each of these values by 5. So now we have a 0.2 chance of landing on 1 times 5, which is 5. 0.4 chance of landing on 2 times 5, which is 10. A 0.3 chance of landing on 3 times 5, which is 15. And a 0.1 chance of landing on 4 times 5, which is 20. Then what we would do is take the expected value, so 2.3, and multiply that by 5, which is what, 11.5, I think. And yeah, expected value, we would do the exact same as we do to the variable itself, always. So if you want to add something to the variable, you add something to the expected value. You want to subtract from the variable, you subtract from the expected value. You want to multiply by the variable, then you multiply the expected value. For standard deviation, you don't do anything if you're adding or subtracting, but if you multiply by a constant, then you multiply the standard deviation also by a constant. So here the standard deviation would be 5 times what it was before. But then the variance, because the variance is standard deviation squared, you don't just multiply the variance by the constant, you multiply it by the square of the constant. So if we multiply all of these values by 5, we don't just multiply the variance by 5, we multiply it by 5 squared, which is 25. So if we were to add 5 to all of these values, then what we would do is add 5 to the expected value and keep the variance and standard deviation the same. But if we were to multiply all these values by 5, we would multiply the expected value and standard deviation by 5, and we would multiply the variance by 25. So here is just some formulas to demonstrate that. This is just a sum rule, sum and difference for expected values. This is sum and difference for variances, which means it's the sum because it's the same thing for variance. And then here's standard deviation. Then this is for multiplying for expected values. This is for multiplying for variances, as you can see by the constant being squared. And this is multiplying for standard deviations. And then this goes back, these three are just things that we talked about last slide, where you add the means and you add the variances. So that's what we talked about here. All right, so here is one that might get a little bit complicated. Don't get intimidated by this formula yet, not yet. So first, I'm going to explain what a probability distribution is as we look at the binomial distribution specifically. So probability distributions are graphs of formulas representing the probability of each outcome when you're running multiple trials. So for the binomial distribution specifically, there can be only two possible outcomes, and the probability of each is constant. For example, one of the classic examples of a binomial distribution would be flipping a coin, right? There's only two possible outcomes, heads or tails. And then you split it into, usually for a binomial distribution, you would classify each outcome as being either a success or a failure. So for the flipping coin example, we could say that getting a heads would be a success and getting a tails would be a failure. Or we could switch it around and say tails is success, heads is failure. Doesn't actually matter. We need to have one success and one failure. So now the probability of success is called P, and the probability of failure is Q. Since there are only two alternatives, P plus Q equals 1. So Q equals 1 minus P. And P and Q cannot change. So you run multiple trials, right? But P and Q aren't going to change. So say we have a coin, and the probability of getting heads is 0.5, and the probability of getting tails, so Q, is also 0.5. Just happen to be the same, but it doesn't have to be. If we flip a coin again, that probability isn't going to change. And if we flip it another time, it's still not going to change, which is what I mean when I say that the probability of each trial is constant. So the reason that we use a binomial distribution, now that we've established what we need to get a binomial distribution, is to find the probability of getting X successes out of N trials, right? So getting a certain number of successes out of a certain number of trials. It says or K here because sometimes you'll see it written as K successes out of N trials instead of X successes out of N trials, but they're the same thing. Here it says X. So this is the formula for calculating binomial probability. It's N choose K, N choose X times P to the power of X times Q to the power of N minus X. Everything that I just said is completely useless. It will be a dead weight. You don't need to know it because we have been blessed with living in the age of calculators. So all you have to do is type this into your calculator. So let me explain. Binom PDF, NPX. That's what it says. Basically, what this means is it calculates the binomial probability for N trials with P being the probability of success. It calculates the probability that you will get X successes. So for example, if we're going to flip a coin 5 times, right, then N is 5. And the probability, if we're saying success is getting heads, the probability of success is 0.5. That's P. So N is 5 because 5 flips. P is 0.5 because that's the chance of us getting a success. And then we want to calculate what the chance of us getting 3 heads out of those 5 flips are. So that means X is 3 because that's a value that we're looking at. So binom PDF, in this context, binom PDF 0.53 would be the probability of getting 3 heads if we flip a coin 5 times. Does that make sense? Does anyone have any questions about that? Because if not, we are going to look at some illustrative examples. No? Okay. So, first off, we're going to say that a light bulb has a 0.1 chance of being defective. And then it asks, what is the probability of exactly 2 out of the 3 bulbs being defective? So, there are 3 bulbs. That means 3 trials, right? So N equals 3. Now, there's a 0.1 chance of a light bulb being defective. And that's what we're looking at. So our probability of, in this case, we're calling it success. I guess a light bulb being defective would not actually be a success, but in this context, in a statistical context, we're going to call it a success because that's the value that we're looking at. So the probability of success is 0.1 because that is the probability of the light bulb being defective. So now we have n equals 3 for 3 trials, and 0.1 equals p because that's the chance of it being defective. What is the probability that 2 out of those 3 will be defective? So now we can take 2 and put that in the x value. And then we would just type this into our calculator. And then we'd hit the enter button and it'd give us out a perfect answer. I, off the top of my head, do not know what it is. And we could plug it into this formula, but that's way too much work. So just know, type this into your calculator and it'll give you the correct answer. Now, what's the probability of 4 out of 4 bulbs being defective? So there's 4 trials, right? We're looking at 4 bulbs in total. So that goes to our n. 4 trials, so n equals 4. Then the probability of a bulb being defective, so probability of success, is still 0.1. So p is 0.1. Then x, because we're looking at all 4 bulbs being defective, x is 4. So now we take this, type it into our calculator, and it gives us our answer. So now we're going to look at coin flip again, but I didn't want it to be boring or confusing. So I said it's a weighted coin. So instead of a regular coin, which has a 0.5 chance of landing on heads and a 0.5 chance of landing on tails, this coin is a weighted coin that somebody would use to cheat. So this coin has a 0.7 chance of landing on heads. So now this one is going to get a little bit more complicated here. We have at least, what is the probability of at least 1 out of the 5 flips being heads? So what we could do is take the probability of 1, 2, 3, 4, and 5 flips and add them all together. But there's an easier way. If you think about this, right, it's saying what's the probability of at least 1 out of 5 flips being heads? That just means what's the probability that it isn't 0, right? Because what's the alternative to this? It could be 1, 2, 3, 4, 5. Those all work. The only thing that it can't be is 0. So instead of adding up all the probabilities of each of the other events, we could just say it's the probability that it is not 0 flips that are heads. So we take the binomial PDF of 5 because there are 5 trials, so n equals 5. 0.7 is a chance of success, so we have a 0.7 here. And then we're looking for 0 successes. Okay, 0 successes, so x equals 0. That's this thing here is a chance of getting 0 successes out of the 5 flips. And then we take 1 minus that, and that's the chance of getting anything but 0 successes, which means at least 1. So now 1 minus binomial PDF n equals 5, p equals 0.7, and x equals 0, because we want it to not be 0 successes. That is how we calculate this probability. So we plug this into our calculator, and that would give us the answer. Now notice, so far we've been using binomial PDF. What that stands for is point distribution function. That's what PDF stands for. Point distribution function. So what that means is a probability of it being at exactly that point for x. Now here is binomial CDF, which is cumulative distribution function. That is a probability of it landing on any value that is less than or equal to x. So if we want to look at the probability of it being 3 or less flips that land on heads, then we would use binomial CDF, still 5 flips. P is still 0.7 because there are 5 flips, so n equals 5. And the probability of landing on heads, probability of success, is 0.7. Now we look at, well, we want 3 or less flips. So x equals 3. The difference between PDF and CDF is if we wanted to see exactly 3 flips, then we would do binomial PDF, point distribution function. But since we want to look at 3 or less flips, we would take the binomial CDF of it, or the cumulative distribution function. What that means is x can be 3 or it can be less than 3. So now, what is the probability of more than 4 flips out of 10 being heads? So probability of a flip being heads, or probability of success, is still 0.7, so p is 0.7. Then we're looking at 10 total flips, right? So n is 10. And then we want more than 4 flips. So that's not including 4. So we could add up probability of 4, 5, 6, 7, 8, 9, 10. Or we could find the probability of it being 4 or less. Sorry, we could add up 5, 6, 7, 8, 9, 10. Or we could find it being 4 or less. And then find the probability of that not happening. So we would take the binomial CDF of it equaling 4 or less, which is basically when n equals 10, because 10 flips, p equals 0.7, because that's our probability of success, and then 4 successes, right? That would be the probability of there being 4 or less successes, since we're taking a CDF, not a PDF. And then we would take 1 minus that, and that would give us a probability of there not being 4 or less successes, which means there would be more than 4 successes. Therefore, in this context, that would be more than 4 flips out of 10 being heads. So if you guys are confused by me doing 1 minus binomial PDF and the 1 minus thing, we could just go back to what we looked at last week, the complement rule. So basically the probability of an event happening is 1 minus the probability of an event not happening. That's the principle that we're using here. We're trying to find the probability of something happening, so we're taking 1 minus the probability of it not happening. So just in this context, the probability of more than 4 flips out of 10 being heads is 1 minus the probability of this not happening, which is a probability that 4 or less flips out of 10 are being heads. So then we calculate the probability of 4 or less being heads, and that is n equals 10, p equals 0.7, x equals 4, the cumulative distribution function of that. So binomial PDF, CDF. So those are just some calculations, some examples for what you would do with a binomial distribution. And now we can look at the summary statistics of a binomial distribution. So I don't know if you guys remember the shape of a normal distribution. It's can't draw with this. Okay. It's basically like a curve, like a bell curve. A binomial distribution is shaped exactly like that, except instead of smooth, it's more like a bar graph that's shaped like that, because it can only be integer values, whole values, because you can't have half of a success, like half of a coin flip. It has to be full whole numbers. So with that, you can find the mean or the expected value of a binomial distribution by multiplying n, the number of trials, times p, the probability of success. You can find the variance of a binomial distribution. That's npq. So the number of trials times the number of, or the probability of success times the probability of failure. In other words, the variance is equal to the expected value times the probability of failure. And then the standard deviation, as always, is the square root of variance. So does anyone have any questions about binomial summary statistics or binomial distributions at all? How do we do it on our calculator? Yep, I was hoping that you would ask that. Actually, I wasn't, because I did not know where my calculator was, but luckily I found it. So I'm gonna see if, can you guys see my camera? Yeah, you can see my camera, right? All right. So what you want to do for binomial functions, right, is you hit second, which is this blue button right here, second. Then you hit vars. And then for a PDF, you hit A. And for a CDF, you hit B. So you can't really see this on my calculator, right? All right, well, for technology is hard. Okay, so you see where it says Binomial CDF and Binomial PDF. If you want to take a CDF, you hit B, and if you want to take a PDF, you hit A. And from there, it gives you this menu. PDF is 1 and CDF is 2. Yeah, that could just be because you have a different model calculator. But either way, the first thing you do is hit second and then vars. And I can put that into the chat too. But it gives you this menu. I don't think you guys can see it, but the first row says trials, and that is where you put your n value. And the second row says p, that's where you put obviously your p value. And then the third row says x value, which of course is where you put your x value. So I'm just going to type it into the chat what you should do. First you hit second. Vars. And that takes you to distributions. And then you hit A, which the way you type that is in alpha and math. So you hit A for Binomial PDF and B for Binomial CDF. So then once you do that, it's going to give you a pop-up menu that looks like this. And then with that pop-up menu, next to trials, you would put, well, it's going to end up looking like this. So next to trials, you put the n value. Next to p, you put the p value. And next to x, you put the x value. All right. So, and then you just hit paste, and it's going to give you the exact probability. All right. So does anyone have any other questions? Thank you for asking that. That is something that is important to know if you want to forget what is the answer to what? The probability of, what I was putting in the chat is just the steps for any question. But if we were to go back to some of these examples, right? We would say a light bulb has a 0.1 chance of being defective, right? So we're going to go to what is the probability of exactly 2 out of 3 bulbs being defective? So this is PDF because it's exactly 2 out of 3. So we're going to go to second vars, and then we're going to hit A because it's Binomial PDF. Then the trials, the number of trials right here is 3 because we're looking at 3 light bulbs. The p-value, there's a 0.1 chance of it being defective. So a 0.1 chance, is counterintuitive, that is, of success. And then the x value, we're looking at 2 out of 3 of the bulbs being defective. So the x value is 2. And then we just type that into a calculator and we get out 0.027. So for these, what are these notations for? These notations are just what you would do, the buttons that you would push on your calculator. Because we went to we don't want to memorize a formula, right? That's unnecessary. So these notations are the buttons that you would push on your calculator. Richard says, can you explain the random variable statement on the addition and subtraction of two set slide? Sure. Let me go back to that. So what this means, right, is if we have two random variables, and we want to combine them, then we can take the mean of the first random variable and the mean of the second random variable and add them together, given that we're adding the random variables together. Now, if we want to subtract the second random variable from the first random variable, you would subtract the mean of the second random variable from the first random variable. If you want to, regardless of whether you want to add or subtract the random variables together, though, you're still going to add the variances. The variances of each random variable, they always add up. Yo-Yo says, if we put it in a graph, what will it look like? What its are you talking about? You can unmute your mic or put it in the chat. The binomial thing. The binomial graph. Okay. That is. So, do you remember what a normal distribution looks like? I can try and find a picture here. But if you remember what a normal, okay. All right, I'll show you. Well, if it helps, a normal distribution is also called a bell curve, if that helps you picture it. Let me just really quickly pull up an image of a binomial distribution. Okay, found one. So, for a normal distribution, right, it looks like this. Yeah, like that. So it's just a curve, just like that. When is a Kahoot? It'll be at the end. We're almost there, I promise. But yeah, this is a normal distribution. Now, a binomial distribution looks exactly the same, except instead of a smooth curve, it's a set of bars. So see those? That's not one smooth curve. They're all separate bars. And that the reason for that is binomial distributions have to be, the values of binomial distributions have to be whole numbers, because you can't have, like we said earlier, you can't have half of a success or a small portion of a coin flip that lands on heads. Whereas with normal distributions, you can have partial numbers because you can have partial data points, like a height. It doesn't have to be exactly a whole foot. It can be half of a foot or some portion of a foot. All right. Are there any other questions? I love that you guys are asking questions, by the way. I appreciate that so much, because what do you mean by bell curve? Bell curve is just the same thing as a normal distribution. How is it formed? How is a bell curve formed, or a normal distribution formed? It's so basically the shape of that curve that I showed you earlier. The height of it is determined by the standard deviation, and the placement of it on the line, placement of it on a number line, would be determined by the mean. But it just looks like this curve. Now, the lower that the standard deviation is, the taller the peak of that curve will be, and the higher that mean is, the further to the right the curve itself will be. But it always just looks like this, and it's formed from data values. And actually, the reason that the normal distribution looks like that is because we can approximate it with a sampling distribution. That is what we're going to get to later today. Actually, we might be about to look at that now since we're done with the questions. But does anyone else have any other questions? Yeah, I understand. This can be, like I said at the beginning of class, this is one of the more confusing concepts of stats. So I'm glad that you guys are asking questions and clarifying. Okay, I don't hear any questions, so I am gonna move on. Okay, yeah, so we just did the binomial distribution. Now we're gonna look at the geometric distribution. So the binomial distribution was trying to find the probability of getting X successes out of N trials. The geometric distribution, the number of trials doesn't matter. We're trying to find the probability of getting our first success on the Xth trial. So with a binomial distribution, we could be, if we go back to flipping coins, we could say we want to find the probability of getting 3 heads out of 5 flips. That we would use a binomial distribution for. But if we want to find the number of flips it's going to take to get a heads, that we would use a geometric distribution for. So what that means is, and it has, first off, it has the same requirements as a binomial distribution. So if we go back, this is when you can use a binomial distribution. This is when it applies. The geometric distribution has those exact same requirements, which is that there have to be only 2 possible outcomes, and the probability of either success or failure does not change in between trials. Now, the difference, like we said with binomials, it's X successes out of N trials. And geometric distributions, that's the probability of the first success being on the Xth trial. Also, the expected value for binomials, it's N times P. For geometrics, it's 1 over P. And the variance is NPQ for binomials, but for geometrics, it's 1 minus P, which is equal to Q. So it's Q over P squared. So now we also have this formula for geometric distributions. This you can memorize because it's a lot less complicated than the other one. 1 minus P, remember, is Q. So it's just Q to the power of X minus 1 times P. But again, you don't have to do that because you can just go to Geomet PDF on your calculator. So first off, the big thing that I want you to take from this slide is it has the same conditions as a binomial distribution, but the difference is binomials are going to find the probability of X successes out of N trials, and geometrics are going to find the probability of the first success being on the Xth trial, trial number X. So I want to reiterate with the coin flip example, but you would use a binomial distribution to find the probability of getting 3 heads out of 5 trials, 5 flips. But if you want to see the probability of not getting any heads until the 3rd flip, right, then you would use a geometric distribution for that. And for that example, since the probability of success is 0.5, and the trial that you're looking at for success is the 3rd flip, you would say Geomet PDF P equals 0.5, X equals 3. So Geomet PDF, by the way, is the exact same as binomial PDF, except it's for geometric distribution and not for binomial distribution. Do stats have something to do with box plots? Yes, stats have a lot to do with box plots. So a box plot is just a way to represent data. So if you have the set of data, there's a couple of different ways that you could graph that. And one of those ways is a box plot. If you want some more elaboration on that, you can go watch the recording of first week, because that's when we go a little bit more into detail with that. How do you solve box plots? I'm not sure what you mean by that. There is no way to. Box plots aren't exactly a problem to be solved, but they are a representation of data. So you can interpret box plots. So what the interpretation of box plots, we break that down more in the first lesson. on the first week, but basically it has two whiskers, and the lowest whisker is the lowest value. The highest whisker is the highest value. Those are the ends of the whiskers. And then there's a box in the middle, and that is the 25th percentile to the 75th percentile, and a line in the middle of the box, and that line is the median. What I mean is the quartiles. The quartiles, the recording for the first week is in the YouTube page of the Discord. So I can send that out after this, but yeah, I can send that out after this. The quartiles, yeah, the quartiles are just, the first quartile is the 25th percentile, which means 25% of the values are below it. The third quartile is the 75th percentile, which means 75% of the values are below it. And then in between, somewhere in there is a median, which is the 50th percentile. 50% of the values are below it. The Zoom recording link, yeah, I can send that to you after class. All right, so now we're gonna quickly look at some geometric distribution examples. I said this was gonna be a short class. Apparently I lied. But yeah, we're gonna look at some geometric distribution examples. So first off, we're going to use the same exact light bulb and weighted coin example, but we're going to use a geometric distribution instead of a binomial distribution because we're answering different questions. So a light bulb has still a 0.1 chance of being defective. What is the probability that the first defective light bulb found is the second light bulb that we test? So now the probability of success here is 0.1, and the value that we're looking at, the trials, is 2. X equals 2. So we would do geomet PDF point distribution function because it's exactly the second light bulb. Geomet PDF P equals 0.1, X equals 2. I can also put in the chat the steps for finding that on your calculator. It's the exact same almost. Just that. All right, you hit second, then you hit vars. Then instead of hitting A or B for PDF or CDF, you hit E for geomet CDF, geomet PDF. Yeah, E for geomet PDF, and F for geomet CDF. If you don't have that type of calculator, yeah, there are online calculators and there are apps. I can see if I can find one of those and then send that out either on the Google Classroom or in the Discord, or have a link for you next class. But yeah, if you don't have that type of calculator, there are plenty of ones that you can use online. So anyway, second vars, and then you hit E or F. And then it's going to give you a table that looks like that. And of course, next to P, you put in the P value, and next to X value, you put in the X value. Pretty self-explanatory there. And then you hit paste, and it gives you your answers. So now we're back to this first example. The first defective light bulb, right? It has, what's the chance that the first effective light bulb is the second light bulb tested? So P here would be 0.1 because that's a chance of success. And then the second light bulb tested, so it's X equals 2. So I'm going to hit second vars. Then I am going to hit E, then put 0.1 in the P spot and 4 in the X value spot, and then hit paste. The answer is 0.0729, in case anyone was curious. So now the first defective light bulb, what's the probability of it not being the fourth? So we can go back to the complement rule. The probability of something not happening is just 1 minus the probability of it happening. So we find the probability of it being the fourth, and then we do 1 minus that. So we take Geomet PDF 0.1, 0.1 and 4 is, and then we do 1 minus that, and we have 0.9271. All right, next, a weighted coin has a 0.7 chance of landing on heads, just like we said last time. What is the probability of the first flip being heads? In other words, it only takes us one trial for a success. So we do Geomet PDF. 0.7 is a probability of success, and the X value is 1, because the trial number 1 is where we have our first success, and it's really just a 0.7. Then what is the probability of landing on heads by the third flip or earlier? If we wanted to just find the third flip, we would do Geomet PDF. But since we're looking at earlier as well, we turn it to Geomet CDF. So again, second vars, then hit E. No, not hit E, because we're looking at CDF this time, we hit F. So now we put in the p-value, which is 0.7, because that's a chance of success. And the X value is 4. And then we just hit enter. It's 0.9919. That is the probability of landing on heads before the fourth flip or by the fourth flip. And then we do 1 minus that to find the probability of not doing that, 0.0081. So because this weighted coin has such a high chance of landing on heads, we only have a 0.0081 probability of not landing on heads by the fourth flip. Okay, so does anyone have any questions on geometric distributions? If not, we're going to move on to sampling distributions, and this part is going to be a lot shorter, and then we have the Kahoot, and then we're done. No, it does not look like anyone has any questions. All right, if you do.
Redo the coin example. I don't really understand.
Redo the coin example. All right. So for geometric.
Yeah.
All right, sure. So if we have this weighted coin, right? It's not a regular coin where the probability of landing on heads is 0.5 and the probability of landing on tails is 0.5, because that's a fair coin. This is a weighted coin, so it's different. And we have a 0.7 chance of landing on heads and a 0.3 chance of landing on tails. So now we want to find the probability of the first flip that we do being heads. So we use a geometric function, right? Geometric distribution. And since it's exactly the first flip, we use a PDF function instead of a CDF, because we're trying to find exactly that value, not that value or less. So now it's the first flip. So that means it only takes us one trial to get success, which means X equals 1. And we still have the same probability of success as 0.7 that we're going to keep throughout this entire thing. So now we do Geomet PDF 0.7 X equals 1. So we just take this and type that into our calculator. And that is 0.7 is what we get out of that. Then for this one, what is the probability of landing on heads by the third flip or earlier? So now we would look at this the same exact way as we did with this one, but it also is asking us the third flip or earlier. So the difference here is it's asking us for just the first flip. This is asking us for the third flip or earlier. So we use a cumulative distribution function, a CDF, instead of a PDF. So now we go do the same thing, but instead of hitting PDF, we hit CDF in our calculator. Then we put in 0.7 because that's the chance of success. And then 3, the third flip, right? So X equals 3. And then we hit paste, and that gives us our probability, which is 0.973. Next, this last example is what's the probability of not landing on heads by the fourth flip? So if we remember the complement rule, it's the probability of not doing something is 1 minus the probability of doing something. So what we would do in this case is take 1 minus the probability of landing on heads at exactly the fourth flip or before. So the probability.
Is there a way for solving this problem without a calculator?
There is. So what you would have to do in that case is instead of putting it into your calculator as geomet PDF, p equals 0.7, x equals 4, what you would do is plug it into this formula. So it would end up being p equals 0.7, so 1 minus p equals 0.3 to the power of x is 4. All of that times p, which is 0.7. So we would have 0.7 times 0.3 to the power of 4. Ooh. Let me put this in the chat. So that's how we would solve that without a calculator. But if you have a calculator, it's much easier to do it with a calculator. So you would just plug it in to here and then type it on your calculator. Geomet CDF. Oh, sorry, this is CDF too. So what we would do for that one, since if we were doing a PDF, we would do it just like I did it. But if we were doing a CDF, then we would have to do, PDF is point distribution function and CDF is cumulative distribution function. So what that means is if we want to find the probability of it being exactly at a value, so taking exactly 1 trial or exactly 3 trials or exactly 4 trials to do something, then we would use a PDF. But if we want to find the probability of it taking that many or less trials, so of it taking 3 or less trials or taking 5 or less trials, then we would use a CDF, cumulative distribution function. So with a PDF, if you want to do it without a calculator, you just have to plug it into that formula. But with a CDF, if you want to do it without a calculator, it's going to get tiring because you got to plug it into that formula and then do it again for every value below it. So 2, 1, and 0. If you wanted to do a CDF without a calculator, you'd have to add all of these up, which is why it's easier on a calculator. So anyway, all right, I'm gonna try to wrap this up as quickly as possible. So that is it for probability. And I think, there's only 2 more, and then we have a Kahoot. So with these last 2 slides, I'll look at them quickly. First off, the normal distribution, we said earlier that it was important for sampling. This is why. Another thing, we used to need to know the z-score for everything, but that's no longer relevant because of our calculators, but it's just good to know what it is. So a z-score is just how many standard deviations a value is away from the mean. All right, so now there are 2 main calculations that you can do on normal distributions, and those are normal CDF and inverse norm. So basically, normal CDF gives you the probability of landing in between 2 given values. So if you have a normal distribution like this one, and you want to take the normal CDF of 1410, 1500, and the mean is 1500 and the standard deviation is whatever that is, right? You would plug all those numbers in and you would hit enter on your calculator, and then it would just give you the probability of being in between those 2 values. Now for inverse norm, you would put in the area that you're looking for and then the mean and the standard deviation, and what it would give you is the number with a given probability to the left. So basically for inverse norm, if we had a mean and a standard deviation, say mean is 1500 with this, Standard deviation, we don't know, but we normally would know. And then we want to find the inverse norm, which is basically the probability, or what value has a probability of 0.1151. That's a chance of landing underneath that value. So we don't really have time to elaborate on this yet, but next week I promise we will go more in depth into this topic. But now normal CDF and inverse norm are the ones that you need to know. And just to be clear, you find yo-yo for inverse norm. Yeah, you would find the area of the shaded area and then you put that in and it's going to give you the value here. So for inverse norm, you're going to put in the mean, standard deviation, and then this area is this thing right here. And then it's going to give you this value. All right. And the way you get to that is the same way, just second, varse, and then for CDF, it's 2, and for inverse norm, it's 3. All right. I know we blazed past that. I promise you we will elaborate on that next class. Then we have a Kahoot after this that I'm going to have to speed up a little bit. And then you guys can go home or do whatever you are planning to do next. But yeah, here's a central limit theorem. So this is probably the most important theorem in all of statistics. And what it says is for a sufficiently large n, the sampling distribution of x bar is approximately normal with mean mu and standard deviation sigma is over the square root of n. What does that mean? So basically, what that means is if we take a sample, right, and we find the mean of that sample, and we take a bunch more samples. Actually, yeah, we will do the Kahoot next week. So yeah, we're just gonna go over the central limit theorem, and then Kahoot's next week. Bet. All right. So if we have a sample, and we calculate the mean of that sample, then we do the same thing for a large number of different samples, and then we plot all of the means on a separate graph. The distribution of those means is going to be approximately normal. So let me back up. Basically, what that means is if we have, say we're looking at the height of all adults in America. I'm going to go back to that example, right? We sample a bunch of random people, and we find the distribution of their heights. Even if that distribution is skewed, the sampling distribution will be normal. So what that means is if we take a sample, right, we find the mean of that sample, and then we do that 30 more times because that's a large enough n, right? Then that is going to give us, if we graph all of the means, that is going to give us a distribution shaped like this, so a normal distribution. And then we can, from there, we can calculate the probability of being in a certain area with this stuff. So that's the reason that the central limit theorem is so important, is even if the data doesn't match perfectly to this, we can take the means of different samples and make it match to this. And then we can use this to calculate different areas and different probabilities using these. So that is, and I promise we will elaborate on this more next week.